Thank you so much, everyone, for attending. Today, we are going to discuss the evaluation of chemical screening tool to predict optimum dosage of natural pozzolans for ASR mitigation. My name is Pravin Saraswatula, and I'm a postdoctoral researcher at TTI. The co-investigators are Dr. Anil Mukhopadhyay and Kai Liu. Let me start by thanking Wang because he gave a wonderful introduction to the topic today. But this problem is real in ASR evaluation. The question is, what replacement level do we test at? Do we start at 20 and then go 20, 30, 40, 50, 60? That's actually not feasible. And the different tests have different pros and cons, but the test which is shortest duration, 14 to 16 days, it kind of has a low reliability in predicting the overall ASR performance. So really, the research effort here was to come up with a scientific approach to determine what is the optimum replacement level that we should test at, or at least come up with a very narrow range, let's say 20 to 25%. If you can establish that, then that would be great. Something that should be scientific and not a regression model, because regression is only good as the data, that background data that you feed into. And something that will also actually attack the effect of soluble alkali coming from any natural pozzolans or new SEMs. If we are able to do that, then I think we have achieved a good comprehensive model for that one. So on that, our first research presented last fall, and it's also currently published at TRR. It was a development of chemical screening tool to predict optimum fly ash dosage for ASR mitigation. So what is a chemical screening tool? It's an approach to estimate optimum SCA for ASR mitigation, and it's not a regression model. Uses two fundamental parameters of concrete mixes, pore solution alkalinity and aggregate threshold alkalinity. And as a rapid and performance-based approach, CST uses water-soluble alkali measurements, which are 1 or 2 days measurements from SEMs to estimate concrete PSA. So basically, it's a 4-step process and very simple, intuitive. First is we measure water-soluble alkalis from different fly ashes. Second, we estimate concrete pore solution. For that, we developed a TTI Model-1, which combines both soluble alkali from cement and SEMs. And third is determination of aggregate threshold alkalinity, which is another version of aggregate reactivity. There are 2 ways you can either measure or predict. And the fourth is finally the screening tool, which predicts the optimum dosage based on optimizing the PSA and THA relationship. So just a flowchart to show the same process again. Cement and fly ash, and finally we determine the pore solution alkalinity using TTI Model-1. Again, this is available as it's published. And the second part is once we determine aggregate THA with one of the process, then this one we developed is as a plugin for the Excel. It optimizes based on the PSA and THA relationship that it's about. So these are the few results that were evaluated in the previous study for the fly ashes. Almost 64% matched with all 3 testing, the long-term ACCT test, ASTM 1567, and chemical screening tool. But in almost 36% cases, 1567 underestimated, as in it gave a lower dosage, but which was not confirmed by the long-term test that we did through ACCT. So as a result, we actually developed this recommendations, which is you first measure water-soluble alkali. The test only takes 1 day. Or we also alternately developed a non-linear regression model to predict water-soluble alkali. The second step is to actually determine dosage by 1567, which is 14 to 16-day test. Then do a comparison between screening tool and 1567. If the replacement level is less than 5%, the difference is less than 5%, then ACC any long-term test for ASR can be considered as optional, but if it's more than 5%, let's say 6 to 10%, then some of the ACCT test is mandatory. So we extended that research to actually evaluate natural pozzolans for ASR performance in the current work. Some of the types are unknown, but most of these pozzolans we received from different sources. Majorly are volcanic ashes except for N4 and N7, which is metakaolin, and N7 I think could be calcined clay depending upon how it behaved. And again, this paper has been accepted for TRR 2023, so published soon. So first, we try to understand what is the mineralogy of these ashes. Natural pozzolans. One thing that sets it apart is it has almost 40 to 90% amorphous content. The another significant fraction is the non-reactive crystalline phases, which are quartz and mullite. But there are also a bunch of feldspar phases, which are like sodium feldspar, albite, andesite, potassium feldspar, or calcium feldspar phases in these. As a result, like whatever alkali sulfates that we measured are relatively very low and also very few in these. Also, it's very difficult to actually quantify alkali sulfates through QXRD. So as a second step, we actually measured the water-soluble alkali. And it's a comparison with all the F and C ashes that we measured in the previous work. We see the bulk of the data for these natural pozzolans is just 1 to 3% of the total alkali. Whereas the class F, it's around 3 to 11, in class C, it's 5 to 17%. So what does this mean? Well, it means that although natural pozzolans are very high bulk alkali, if we actually evaluate it through stoichiometry, almost 17 to 65% of those alkalis are actually in feldspar phases, all the albite and microcline phases that we talked about. So they're insoluble, they're not available for the reaction at all. 1 to 3% are actually water soluble, which are instantly available. So that leaves approximately 30 to 70%, which is coming as a result of pozzolanic reaction. But this is only one phase that actually explains the alkali effect of alkalis on ASR performance. The other is if we actually see this calcium and silica ratio of the ingredients, the natural pozzolans have very low calcium to silica ratio as compared to F and C. So as a result of pozzolanic reactions, the hydration product, the CSH or the CASH that is formed, is pretty low C by S ratio, so it has a very good alkali binding capacity. And so that actually explains the available alkali measurements that we did through ASTM C, where after 28 days, we only saw around the available alkali to be 11 to 16% of the total alkali. Whereas for class F, it was 25 to 50, and class C went as high as 60%. So then we applied the screening tool to actually understand like what could be the possible replacement levels, and this is just all things put together at one place. So the green line estimates the aggregate reactivity. We selected R2 for the test. So we can see that approximately like 25 to 30% could be a good replacement level based, which explains like the PS where the PSA could be less than the THA. But for a similar aggregate, around 30 to 35% of the class F ash should actually be able to mitigate ASR. But once we look at class C ash, we go all the way up to 40 to 50% to actually get that effect. Also, hold on, emphasize, the screening tool is just not for one aggregate reactivity. You can compare a bunch of different aggregates with different reactivities in a similar way and try to understand like what is different values that you can come up with. If not one value, then a bunch of values. So just for these, it's not pozzolan fly ash dosage, it's natural pozzolan dosage, but for these natural pozzolans, we actually estimated what could be from the screening tool, and it came out to be around 27 to 30%. So exactly performed both 15-day 1567 as well as ACCT ASR tests for these ashes, and they actually are less than the threshold values in all cases. So what are the conclusions from this study? Is all natural pozzolans here meet class N, but that does not talk about anything in terms of their ASR performance. But based on QXRD, the natural pozzolans primarily composed of amorphous content and bunch of alkali-bearing crystalline phases, which are feldspar and mica, and non-reactive crystalline phases. The presence of alkali sulfates are really difficult to detect in QXRD for most natural pozzolans. And this is pretty important that most of the natural pozzolans have significantly high levels of bulk alkali, 3 to 8%, but only 30 to 70% are actually coming as a reaction of pozzolanic, as a result of pozzolanic reaction of amorphous phase. 17 to 65% is bound, which is not in feldspar phases, which is insoluble and not available for reaction at all. So basically the effect of low availability from pozzolanic reaction combined with low WSA measurements actually kind of understand like why we see a low available alkali, low level of available alkali from these natural pozzolans is because the combined effect of slow release as well as low C by S CSH which actually consumes. So there is very negligible net alkali contribution into pore solution. The CST predictions were favorably validated by both ACCT as well as the AMBT test. Although AMBT test is not recommended for any SCMs where the bulk alkali exceeds 4.5%, but since the water soluble as well as the available alkali are pretty low, it justifies the use. So as a next step, we are actually doing a comprehensive durability evaluation where we actually evaluate each of these aspects. We are currently halfway through the reactivity, fresh properties, and durability evaluation. And the previous presenter actually also pointed out to this test, but we have taken a slightly different approach with that. We measured the reactivity from the R3 test and also saw the calcium hydroxide consumption, and based on it, we are able to distinguish if it's a pozzolanic or a hydraulic behavior, or if it's less or more reactive. But the question is, how do we apply this to actually evaluate ASR performance? And this is like still preliminary, but we're still working on this. The idea is currently screening tool only uses water-soluble alkali or alkalis to actually estimate optimum dosage, but we are going to extend that and include the reactivity data to make a comprehensive approach on estimating optimum replacement. And how do we do that? If something is hydraulic or pozzolanic, we get it from the calcium hydroxide consumption. So based on that, it actually talks about what is the potential for a formation of like low C by S CSH. So that actually indicates the alkali binding capacity. Based on isothermal calorimetry, we get more reactive or less reactive. It can indicate like what is the amount of hydration product that can form. And finally, water soluble alkali talks about like what is the amount of soluble alkali that is coming out of SCMs. So when you put all of them together, then this is the kind of estimate that we can develop. Still preliminary, and we're still working on that. And some of the other data would be presented tomorrow in another session, I think between 4 and 5:30, as an alternative SCMs by Professor Dr. Anand Popadhyay. So we want to thank Texas Department of Transportation and the others who sponsored this project and also gave us the materials. And thank you.